This is a dramatic reading of Deriving the Maxwell Homogeneous Equations using Quaternions, the third of 5 blogs in this particular little micro mini series, blogs by the Stand-Up Physicist, available at science2.0.com. Nature abhors a magnetic monopole, although she adores gravitational and electric monopoles. The homogeneous Maxwell equations are the ones that need no currents. They're known as the no magnetic monopoles rule, or law, I guess, and Faraday's law. There are 3 ways to derive the homogeneous Maxwell equations. The first way is to use vector identities. Now, that's actually the simplest way, and so that is very widely used. Pick a particular way to write the electric and magnetic fields, and the job is basically done. The divergence of a curl is a long way to say 0. Define the magnetic field as a curl, and its divergence is 0. And then there are no magnetic monopoles hiding behind the couch. The second approach is to use differential geometry power tools, filled with the goblins of tensors and dual vector spaces and exterior derivatives. Only math knights can survive such a passage. The most important theorems in differential geometry are recruited to do battle. Anyone calling themselves a mathematical physicist will have mastered this approach earlier in their career. I can't really be your guide for such a quest, since I'm not really the stand-up mathematical physicist. The third path uses the 3-part harmony as in the previous blog. Pick a Lagrange density wisely, apply Euler-Lagrange, and then choose a gauge. Well, actually, that third step can be skipped, really, because I'm actually foreshadowing something here. I will use that same line again for my GEM unified field equations derivation, the 5th and final blog in this mini-series. Logical consistency is good. The Lagrange density technique for the homogeneous equations is not actually widely known. The reason, I think, is that it's not in the good red book. This is called Classical Electrodynamics by J.D. Jackson. Oh, and I should point out something. He's come out with volume 3, which is blue. Okay, so this actually dates me. If you go and buy your own, it'll be version 3, it'll be blue, and who knows, might turn green by version 4. I liked red, man. It was dramatic. All right, anyway, here's what he wrote in that particular edition. The Lagrangian equation 12.85, I mean, this guy goes through a lot of equations, right? Yields the inhomogeneous Maxwell equations, what I've been calling the source equations, same thing. All right, but not the homogeneous ones. This is because the field strength tensor F alpha beta was chosen in terms of a 4 potential A lambda, so that the homogeneous equations were satisfied automatically. Rock on. Now, Jackson went, for door number 1, the vector identities. And I don't know, this doesn't sound so great to my ear. Be clever and you get the desired result. It is true, all right? It's just not the answer to the question raised, which was to find a Lagrange density that generates the homogeneous Maxwell equations. That's it. Well, so what Lagrange density would give me the 2 homogeneous Maxwell equations? I actually had no clue. But I did actually have one clue from Jackson here. Okay, because he made this point. He said, there are really only two things made out of these E and B fields that are invariant under a Lorentz transformation. One is B squared minus E squared, and the other is E dot B. Okay, the derivation of the inhomogeneous or source Maxwell equations used the former, the B squared minus E squared. Wouldn't it be really cute if the E dot B, the dot product of those two fields, ended up generating the homogeneous Maxwell equations? So I decided to investigate that. I didn't know, all right? But I wanted to kind of find a different road to that dot product. So the starting point is like I've always been doing, in this little mini-series, that I want to write the two gauge-free Quaternion derivatives of a Quaternion potential. Oh, that sounded complicated, didn't it? It's not, okay? I basically take that del thing, which is a 4 derivative, acting on a 4 potential, and I subtract away the scalar thing, and what I end up with is the typical definition of E. Okay, it's minus E, because it's the time derivative of A and the gradient of V, and then the curl of A as the B field. And if I switch the order of the A and the del there, subtract away that scalar as I did before, then I get minus E and minus B in the 3 vector. So that's always my starting point. Okay, so then I said, well, how do I just get a dot product between those two fields if that's kind of my starting place? And it's my starting place because it's like really a complete survey of how a 4 potential can change in 4-dimensional space. I really like completeness. So what I did was I took the norm of these two different ways of writing the Quaternion differential acting on the Quaternion potential, and you can see you get an E squared and a B squared in there, and then you just but you do have these two different dot products in there. So if we subtract one from the other, then we end up with nothing but E dot B. Okay, so the dot product there is often 0, because if E is 0 or B is 0, or they could be at right angles. Of course, in other situations, it's not going to be 0. And so, like last week, I know that's the Lorentz invariant. I just don't really have a nice short demonstration of why that is so. So the Euler-Lagrange equation, eats partial differential equations for breakfast, whether they happen to be 0 or not. So write out this Bx, Ex by its component parts. And so we start with the definition of the magnetic field that I learned way back in high school, writing the I, J, K, the derivatives, and then the potentials, so that I can remember that it is positive dAz dy minus day dz. And here is the definition of the electric field. Easy to remember because it's all x's, and so it's got to become these kind of combinations: the time derivative of ax dt and minus d phi dx. And so you just want to multiply those two together, and that's basically high school algebra that looks more scary simply because because we've got more symbols for involved, but it's really not beyond a high school student's courageous skills. And then if you want to generalize this for the y and the z directions, well, you just kind of do exactly that. You generalize, and what's kind of fun is by the time you get down to the z terms, you can actually check to see if you're right or not, because it's like you've got to have kind of Sudoku rules in play such that, well, if you didn't cover that one in this position, well, then you have to, you actually have to. You need a new kind of thing in this in a particular slot. So there is no current coupling term this time. We were taking the difference between the two norms. That will also take the difference between any kind of current coupling terms, and the resulting subtraction will leave a scalar that is 0. Now, the 3 vector actually is not 0, so the equation does not actually have to apply to a vacuum, which is kind of an interesting area for further research, I think. So here is the proposed Lagrange density for the Maxwell homogeneous equations in all its component parts. Now this week we only have 16 terms versus 22 needed for the source Maxwell equations. All of the terms have this kind of what I call maximally mixed quality. There's one part from a scalar, either the t, d by dt, or a phi. And there's one part from the x, y, and z's kinds of slots. So it's either an ax, a y, a z, or it's the differential of those three. And half are positive, half are negative. It's like this perfect setup for cancellation. And there are no terms that are squared, and no factors of 2 to keep track of. All right. So here's a mini refresher on putting the Euler-Lagrange equations to work. Do simple things one at a time. So for the first equation, we're only going to work with phis, and we basically end up doubling up these derivatives, and that's about it. So we're going to take this, let's just go ahead and do it. So here's the phi terms, and this is kind of nice because it means you can ignore half the terms out there. I like that. Ignore a lot. So that's all well and good, and we'll notice that we can get terms that cancel, because you see one of these d phi dx's, when we take a derivative with respect to d phi dx, we'll end up with a second order mixed derivative that's a derivative of ay with respect to x and z. Now follow that red arrow, and you say, what's that going to generate? Well, nothing when you take the derivative with respect to d phi dx, but when we take the derivative with respect to d phi dz, okay, we're going to get a second order derivative of y with respect to z and x. Oh, and look, the first one was minus, this one's plus. Those will cancel. And so those red arrows show the signs that the terms that are going to cancel each other. We can look to see then how to summarize this result. And if we just go across the top line, we see we can pull out a partial with respect to x, and that leaves all these z's and y's, a y, a z, and it's like, oh, that's right, that was bx. So this is the derivative of b with respect to x, and so we basically end up with this del dot b equaling 0. And that is, in fact, the no monopoles law of Maxwell. So now we repeat the process, but we focus on the terms with ax, and you can see they're kind of in more places than the first law. And we're going, ooh, are these going to cancel? And again, we can look and say, okay, look at those ax's. What's downstairs? Oh, there's a chance. And the red arrows are trying to point out what terms are really going to run into each other and end up canceling each other out. Now, figuring out the summary statement is more tricky here. We just look at that top box and, well, it's a time derivative of something. What is it? Oh, that's the bx thing. So it's the time derivative of bx, and then this thing below it, there are these two boxes, and I think the only thing you can do to figure this out is to take the curl of E and say, hey, that's actually going to be the curl of E. I mean, it's kind of like I don't see an easy shortcut on that one. All right, so it's just an amazing thing that Faraday's law works. So we summarize along the boxes, as it were, but the cancellations kind of jump between various lines, and this total summary is that dB, the time derivative of the magnetic field minus the curl of E equals 0. So if a reader is actually familiar with a vector identity, you should be able to see the same thing at work. I mean, it just feels deeper to me because the Lagrange density kind of gets blended into that vector identity via Euler-Lagrange. So we have this graphic representation of the derivation of all four Maxwell equations all at once. As we can see, these are two distinct Lagrangians. That's what those dots and circles are up at the top. The one we dealt with this week, she's the stuff for the B field, which is kind of the solid yellow boxes. No, that's the E field. Solid yellow boxes are the E field, are right next to the B field sort of stuff. And for the homogeneous ones, the ones with all the red arrows, the ones that cancel out, the no monopoles, the Faraday's law, it kind of almost makes sense. They're kind of so close to each other, the electric and magnetic field. They're interspersed, they're interdigitated, and they go and cancel each other out. Whereas the source equation, we put your B field on B field squared on one side, you put your E field squared on the other side, and Gauss's law is just pure E field, and Ampere's law takes some of the E field and some curl of the B field, and that gives you that law. Now, I should admit my own kind of personal point of vanity, a point of excessive pride. Maxwell is the #1 physicist in a list of those that are unknown to the general public. Maxwell worked in a time, before electric lights, let alone computers. He was just so bright. He figured out that Saturn's rings had to be made up of particles so that the system could be stable in a mathematical sense. I've got no idea how to approach such an issue. I suppose I could look it up. And here's a quote about that accomplishment. It is one of the most remarkable applications of mathematics to physics I have ever seen, according to George Airy in the day. He also made contributions to the study of color. I think he made the first color photograph, and dimensional analysis. And then, of course, there is a treatise on electricity and magnetism in 2 volumes. I audited a graduate level class at BU that used good old Jackson here. And in that semester, I decided, to look at the old book, which was really a tough read because he used German notation for everything. I still actually recall, though, that I saw one of the homework problems that was assigned in Maxwell's treatise. And I just had this sense, not that I did a close study, that Jackson is just kind of this Americanized modernization of the treatise. How true that is, I'm not really quite sure. I would take a careful reading of the 2 works, but just a general feel it was like that. Now, Maxwell did want to incorporate Quaternions into his work. Recall that Quaternions were an important and popular subject in the day, instead of just this historical footnote. He had taken classes, after all, with Hamilton himself. And Hamilton was a guy who coined phrases like dot product, cross product, div, grad, curl, and all that to describe the math of quaternion multiplication. And his good friend Tate actually wrote extensively about quaternions. The first edition did have 2 sections with quaternions in the title, and you can actually look at edition 1 on the web with a little bit of work. And in those sections he used pure quaternions, ones where the scalar is like set to 0. A pure quaternion is, functionally just no different from a 3 vector. So he wasn't really exploiting the properties at all. So my own feeling of excessive pride comes from accomplishing something that Maxwell, wanted to get done. No, this does not mean I work at his level, okay? Equally strong in my heart is just, how absurd this particular technical feat is. I mean, I'm so clumsy when doing physics. I can, however, be really great on a puzzle where there's just this one little clue that I read about a decade ago and I can recall it, okay? Because that BU class I took sometime in the mid-90s, all right, when I'm not so good with my own history, but I started to do this Quaternion derivation of the Maxwell equations, well, actually in the late, I'm thinking somewhere around 2008, okay? So there's a decade, if not more. And, it was that one fact that I went on and said, boom, there it is. I consider this a rediscovery that there's probably somebody out there that already knew this, okay? So it's not like, whoa, everything changes. Although they wouldn't have written it with quaternions, okay? And that to me is much more of this, what's the word? Isomorphism, up to an isomorphism. In other words, if somebody did E dot B, I could say, hey, and I did that up to an isomorphism with quaternions, which means I did the same thing. It's got a slightly different name, but it's not like, not really new, okay? So, but I don't know. It feels like I can make progress on impossible puzzles. It's a skill I have, but it's not going to pay any bills. So I recommend to you that you do this with your own pen and paper. Time will just like slip away as you watch these patterns intertwine. It's really kind of neat. And leave those calculations when you're done on your desk, because people will presume you are the smartest person they know. All right, so here's my snarky puzzle, and here's again, being honest, I asked this, and I thought, wow, this is really cool, and then somebody questioned me on it, and I go, oh, no, that question is just wrong. It's just wrong, and I'm going to leave it as is, saying this question is wrong. Find out why it's wrong, okay? Because that can be a good thing too. So what I asked was, take one of the Quaternion derivative ways to write the E and B field. So that'd be one of these 2 guys. All right, square it. All right. Now notice that the scalar is a Lagrange density that will be able to generate all 4 of the Maxwell equations via the Euler-Lagrange equation. Oh, correction. No. That actually is not true. Okay, but figure out what's wrong with that. All right. So for a math overdose, I mean a serious math, scary as shit bonus problem. All right. This thing, when you take this guy, all right, that guy there, he has a phase, all right, so just do something with it. I mean, it's not 0, okay, so if nature uses this for 2 of the 4 Maxwell equations, Well, maybe she might be toying with the 3 vector. So see if you get anywhere. All right. Thank you very much.